Hey, Mikey.
Afternoon, sir. Afternoon.
Hi, Mikey.
Even, sir.
How you do?
Not bad enough.
Nice, nice. All
Yeah,
right.
man.
Just waiting on the others to come. I just give them a few more minutes, and then I'll begin here.
Okay, yeah, man. No problem.
Good afternoon.
Hi, Karen.
Afternoon.
Hold on. So the rest of them now come class tonight? That's what I'm to understand.
Well, no one sent any communication that they were going to be late or anything. So,
All right, do me a favor. Let us go with I want to see the structure, just to recap what it is that we did the last time of aluminum oxide. Look at your periodic table. We're going to do the structure for aluminum oxide. In the meantime, because I'm going to start the covalent bonding in a few. Aluminum oxide. Carly, got that?
okay, sir.
Yes, sir.
All right, start for me, please.
Sorry, I'm not like that one. I give one kick it.
Exactly. See, it can kick me too.
Sorry, I know the answer, but to get to the answer, that's my problem right now.
But I don't understand why though.
Alright, so
What's the electronic configuration of aluminum?
electron, alright, so it's 2, 8, 3.
3.
Right.
Yes, sir.
And the electronic configuration for oxygen is
2 to 2,6.
6.
And
So it would be easier for oxygen to accept 2 to balance out.
Yes, and it would just leave back 1 for the aluminum.
so
Say that keep me.
so continue.
Alright.
So let us work it through. Aluminum has 3 to give. Agreed?
Yeah.
Yes,
yeah.
sir.
Oxygen has 2 to accept.
2 to accept, yes.
That means aluminum can have 1 extra one, don't?
Mm-hmm.
Yeah.
But aluminum can't give up 2 and keep 1. It have to give up everything, don't?
Yeah.
Yeah.
So what are you thinking? What are your thoughts now? Now that I said that.
You just give it the full, give it all 3.
If I clap it today, see? You remember oxygen can take only 2.
Yes, sir.
Good. So
So it
oxygen
only
can't
give
take
2.
Huh?
It only can give up 2. Because oxygen can't take more than 2.
Which is the point I'm making. So oxygen can only take 2. So aluminum will give up 2. Aluminum has how many more left?
1.
1.
Okay, so what aluminum needs to do now then?
Try to find somebody else to give it to.
Yeah.
But I never asked about somebody else. Why can a third party into the relationship? I said aluminum and oxygen, and you want to carry somebody else in there? You're a cheater.
No,
what I think aluminum should do would be so them have 1 there so for be stable. And then could share and give
ET
2.
or ET?
Right. So there is no sharing because it's an ionic bond. In ionic bonding, there is no sharing.
No sharing. You either take or you go on.
Right. So what do you think?
Them keep the 1.
They cannot keep it.
Oh,
They have to give
can't
up
keep
everything. No. So put it this way. Once you get into the relationship, there's no turning back. So you can't have 1 foot in and 1 foot out. So
basically, I would just then if they give up, if they give oxygen to them, just have to just allow the final one to just like be absorbed or just disappear.
Disappear how?
Oh. Mm. Oh, could it be that it could be it can become like a some form of like an isotope or something like that?
No.
No. Other one me can't get rid of him. That single one. I mean, I try to get
put it
rid
this
of him.
way. Let us put on our thinking cap. How many oxygen needs?
2.
2.
2 is what kind of number?
Even number.
Okay. How many aluminum has to give?
2.
Really?
Oh, 3. Sorry, 3.
Them have an odd number. 3.
3 is a what number?
Odd number.
3 is an odd number.
How can I make that number even?
Subtract. Add.
Multiply.
By?
Multiply by the 2.
Okay, I'm gonna do that. What I have?
You get 6.
6.
Okay. Now, so I have 6 now to give. But oxygen can take how many?
Only 2.
Okay. So how many oxygens are we gonna need then?
How many oxygen you gonna need?
Yeah.
You're gonna need 3 oxygen.
Okay, great. And how many aluminums are we gonna need?
2.
Okay. Have a wonderful rest of the
Okay.
What?
Uh, all right, sir. We're gonna do it outside the future.
So.
Harley, understand what to do?
Yes, sir, I'm doing it.
Okay, great. Great, great, great. All right.
All right, sir. It kind of look odd, but it did it.
Okay, what is a formula for aluminum oxide nowadays?
Al
Ooh.
subscript 203. The
Very good.
subscript 3, yeah.
Very good. So AL203.
Yeah. So sorry,
Excellent.
you see from I do it
Um,
that way there where me identify like how much oxygen, how much to balance it out and me get it balanced. Equation supposed to
mhm.
balance really and truly. Yeah, it does jump out.
Yeah, yeah. And you have to think outside of the box because remember now, if it's aluminum, if they have three to give, them not gonna give and all back.
Yeah,
Them are gonna give and give everything. So they all the once you talk about ionic bonding, the metal, all the valence electrons in the metal must go. So them can't say, yo, I'm gonna give you, I'm gonna give you, I'm gonna give you two and keep back one. No, it has to go. Has to go. Not way work like that. And then no, the oxygen, if it is accepting, it is going to accept as many as you possibly can. So if oxygen is accepting from aluminum, but aluminum has three to give, but oxygen can only take two. Oxygen are gonna say, yo, oxygen, come here. Um, we are going to one deal, you see, and me I will give you some other electrons in order for it to become stable. But when the other oxygen come now, the other oxygen I say, but I want it to give. And oxygen not gonna say, no man, aluminum, go and call it twin brother. Because it's painful for the atom, It's painful for the atom because remember the atom is the number of protons equals the number of electrons.
yeah,
So in short, there's gonna be already a strain, and that's why it becomes an ion, and that's why it is so reactive. Right? So it's aluminum will say, yo, never mind, man. I'm gonna call me twin brother. Call him twin brother, and then no aluminum no longer has three to give, but they now have six. And oxygen say, yo, that's fine, man. I'm going to call my triplets because me can take two, and my two other siblings now going to take two each. So it must be balanced out in that way. It must be balanced out. All right. I'm going to give you another one in the meantime. Um, so you finish that one, Michael?
yeah, man. Finish.
All
I
right.
just send it to you.
No, don't send it yet. Hold it with this one. Karel, you finished doing that one?
Yes, sir.
All right, good. All right, I'm making up another one to give you. Um, say, uh, I'm gonna give you. I give you calcium chloride already.
Calcium,
Yes,
yeah.
sir.
All right, I'm gonna give you aluminum chloride. Aluminum chloride.
Mm, that's a
Think
good
of
one.
this. Think of the same that I told you a while ago. Aluminum chloride on the
Yeah,
market.
that's a good one. From here, we know say I want next trouble one. Aluminum chloride.
Only so silent. All right.
Yeah, man. uh, it's yeah, man. I'm good. I'm good. So it's ALCL3.
ALCL3 is correct. So, Carol, what you got?
So you
In
want
the
to see me
same thing, sir.
how me maneuver them three atom here for sure the share in the elections. I
Say, say it
turn
again,
chemist
Mikey.
now.
Say it
Sir,
again.
you want to see how we maneuver the elections for to show the difference the
Transfer.
movement of the transfers.
Nice. Nice. Nice.
That's the
Nice.
only way, because you see, if I try to do it the other way that them show on YouTube, I'm not gonna
Mm-hmm.
get it. But doing it this way, I know that hey, you have to balance out the way here, and the only way to balance it out is to ensure that every atom have 8 in a ring. 2, then 8, then 8, then 8.
Very
According
good.
to this part of chemistry.
All right. Very good. I'm happy that you get. Where's Carol though? Carol?
Yes, sir, I'm here.
Or you stay. You're able to do that one?
Yes, sir.
All right. So do me a favor. I want you to take a photograph. Both of you, I want you to take a photo, just like what we did for Erico. Take a photograph of it and put it in a Word document and send it off to me, please. I can mark it. I want to see what it is that you've done. You follow what I'm saying? Michael know what to do already,
Yes,
but
sir.
you follow what I'm saying, Karen?
In a Word document.
Yeah, just Mikey, explain to her what to do, please.
Alright, so you remember how we normally just when we get the assignments in a pre-calculus, we take the photographs and then put them in our Word documents and email them?
Mhm.
Yeah, same thing.
Also, it's
So you add,
just putting the photographs that you took in Word document and then emailing them.
yeah, correct. So
Yeah,
Okay.
but instead of emailing that one, you can just attach it to you can send it to me to everyone, or you can send it directly to me over Zoom here. I can download it from Zoom since I'm here in the
yeah.
class. Follow me, Karen?
Yes, sir.
All right, cool. Harold, Orpan send something now?
So if something for email it to you again?
It says email it?
No, no, sir. We can't send it right here.
Yeah, man, send it right here.
Okay.
Seriously, so the beautiful, when I realize now when this reaction happen, you end up with each atom for the aluminum chloride. So the electron configuration becomes, for the chlorine, you have 2, 8, 8. And for the aluminum, no, sorry, 2, 8. And for the aluminum, you get 2, 8, no, I do it the right way and stop. So for the chlorine, you get 2, 8, 8. And for the aluminum, you get 2, 8. And then for the aluminum, sorry, hear me? Sorry, you hear me? Hold on there.
Sorry, I got disconnected a while ago.
Oh,
So I was saying to you, you get 2,8 for both of them.
yeah.
Mm-hmm. And that's
And
why it
that's how I
become
know that I do it properly.
right. And that's so and that's also now, you know that it is you have because it's no stable. All right. Sorry, that thing didn't happen. So let us continue. I want to okay, give me now. I'm just saving the document here because I want to move it covalent bonding now. I'm use and send off to you. All right. So most documents saved. Allow me now to talk about some covalent bond. So let me share this one here. So we have been introduced to something that is called ammonia. Anybody remembers the formula for ammonia?
Well,
Na3.
NH3. Now, both nitrogen and hydrogen are non-metals. So because both are non-metals, so they will undergo covalent bonding. Right? So covalent bonding occurs between two non-metals. Metallic bonding occurs between two metals. Ionic bonding occurs between a metal and a non-metal. So once you talk about a covalent bond, it is two non-metals we're talking about. Ionic bond, a metal and a non-metal. Metallic bonding, two metals. All right. So what is the electronic configuration of ammonia, of nitrogen, I'm sorry. Nitrogen is what number element? Nitrogen is what number? What's the atomic number for nitrogen? You need to know the periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, then oxygen. So
Sir,
nitrogen is what?
seven. I'm trying to
7.
unmute.
Yes, 7.
7,
Right.
sir.
So therefore, since it's 7, the electronic configuration is?
So it will be 2,5.
Good. And hydrogen is?
1.
Mm-hmm. What's the electronic configuration?
1.
1. Good. That was a trick question.
Yeah.
All right. So now you recognize hydrogen is in a pickle because hydrogen needs one more electron in order for it to obtain a stable octet or a stable energy level, because it has 2 electrons on a K shell. It has only 1 shell. So it needs 1 more electron in order for it to obtain stability. Can you see that?
Yes, sir. So it would have the first ring, first energy level, and it needs 1 more to actually balance because that has a limit of 2.
Right. Nitrogen, on the other hand, no. Nitrogen has 5 valence electrons. Do you think that it will give up those 5 electrons?
No, it wants 3 more.
It wants 3 more. So Nitrogen can
Well,
actually
sir, hold on,
go
sir.
ahead.
Sir, in the case of with hydrogen, it wouldn't give up those electrons because it has more. But in the case, say for example, chlorine, it might as well just give up the 5. Just because it has more. So the bigger number bullies the smaller number, basically.
Right, but chlorine, but nitrogen though has 5 electrons. It is easier for it to accept 3 than to give up 5. So that's how you look at it. It is easier for it to accept 3 electrons than to give up 5. The energy required to receiving 3 electrons is far less than to give up all 5. You follow me?
Yeah, yeah.
The energy in chlorine to give up those 7 is far less than the energy to accept 1.
Yeah, that's true.
So the energy required to give up those 7 electrons may destroy the chlorine atom. You follow me? I don't
Yes,
want
sir.
to destroy the chlorine atom. So chlorine say, yo, you're the plan, I'll accept. So chlorine can take place in an ionic bond, which is the point I'm trying to make. Chlorine can take place in an ionic bond. And chlorine can also take place in a covalent bond. Because it can share with other atoms in a covalent bonding. Or it can accept electrons in an ionic bond, as in the case of sodium chloride. Follow me?
Yes, sir.
So look at this here now. What's the mass of nitrogen?
The mass is 14.
14. Ah, that's 9. So it has 9 neutrons and 5 protons in order to get that 14.
Huh? Repeat that, sir?
So 7 and 7.
Yeah, 14. Yeah,
14.
I did
yeah,
have
so
to say if
7.
you're paying attention. I did to say if you're paying attention, but it's after I said that you say, huh?
Okay. Yeah, because I was like, what?
All right, so electron configuration is going to be 2,5. So that's 2, 1, 2, 3, 4, 5. Do you agree with that?
Yes, sir.
All right, no. So this is what they call the dot and cross That's a dot and cross diagram. So one atom is going to be used to represent the cross, and I use the other one as a dot to represent it. Now, let us look at our hydrogen. How many electrons hydrogen now has in its outer shell? This one.
2.
2. So hydrogen is pretty much stable this way, don't it?
Yeah, man,
Yes,
very
sir.
stable.
And it has 2 more right here, so this one's stable too. And this one has 2. How many electrons nitrogen now has in its outer shell? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. So
That's stable too.
this stable now, yeah. So the charge of this on this compound is neutral. It's 0. Has a 0 charge. Neutral. Follow me?
Yes, sir.
Karen, how you stay?
Yes, sir.
All right. I'm going to give you a quick one. A quick one. I want you quickly to do for me. All right, so some of these compounds occur as diatomic molecules. For example, hydrogen is diatomic. Oxygen is diatomic, meaning that 2 of the oxygen can bond together. Chlorine is also diatomic. Nitrogen is also diatomic. So I can have my oxygen gas O2. So my oxygen gas O2. Let us see. Oh, come on.
So diatomic, what you said exactly?
Molecules.
Molecules.
For example, oxygen gas, O2. So it means that you have 2 oxygen atoms coming together for that. So therefore, the electronic configuration of oxygen is 2,6. Agreed?
Yes, sir.
Mm-hmm.
Sorry, you share something else?
Rockstone. Tell me that you've seen it now.
Yeah, I see. Yeah.
Yeah, sorry about that. So you have one, two, three, four. 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense?
Actually makes sense now, because I was there wondering, how you gonna make this work? It makes sense now.
Yeah, man.
Yeah, because both of them have 6 in the outer shell.
Right.
I was like, no man, so how them are gonna share now to balance it out? Because I didn't know that sharing would have allowed them, even though them have them shorter so much, to balance it out.
Mm-hmm. One, two, three, four. Right. So if you look at it now, so I'm using my dot and cross again. So that's why I was erasing it. So I could get the stuff. Let us look at the dot and cross again. If you look at this oxygen atom, oxygen has an electronic configuration of 2,6. Agreed? 8 electrons in total, right?
Yeah.
All right. And the mass number is 16. Agreed?
Agreed.
So it has 8 protons and 8 neutrons. Agreed?
Yes, sir.
So now the valence electrons for oxygen is going to be 6. So watch my 6 on this one. 1, 2, 3, 4, 5, 6. Do you see those 6 for this oxygen?
Yeah, I do.
All right. And let's just count the other 6 now. 1, 2, 3, 4, 5, 6.
Mm-hmm.
But for the diatomic molecule, you're going to have oxygen sharing these 4 electrons, each upside of each other, being shared. And then you're going to have 1, 2, 3, 4 on this side, and then 1, 2, 3, 4 on that side. So this is now going to be my O2 gas. And this is how my oxygen links
Repeat that one more time, sir.
Repeat what? Which one?
The
diatomic?
Yeah.
Right. So I'm just saying diatomic, meaning that when I have a diatomic molecule, it means that it is an atom coming together with an atom of a similar kind, creating a bond. So I can have hydrogen gas. Hydrogen and hydrogen give me that diatomic molecule of hydrogen. Oxygen coming together to give me that O2. Nitrogen can give me the N2. And we are going to be looking at the nitrogen cycle, and you'll see how nitrogen is produced in the atmosphere. So that is diatomic. Fluorine is also diatomic, CO2 gas. Bromine is also diatomic. Iodine is also diatomic. So there are several of these compounds, atoms, that can actually bond covalently with one of its kind to form a diatomic. Di means 2. Atomic molecules. And it's molecule because it's more than 1. You follow me?
Yes, sir.
Right. So you have to be very careful in how the bond is created, or you do the bond, the sharing in the diatomic, because you recognize that oxygen has 6 valence electrons. It really wants 2 more. But both oxygen want 2 more. So them say the plan. Come together. And the 2 you want, I will share 2 with me, and then you share 2 with me. So both of them are sharing 2 electrons to make up those 4 electrons, and then the other 4 electrons that they have are standalone. Does that make sense?
Yep, perfect sense.
Karen, or you feel about that now?
No, sir.
What he said? He said no?
Yes, sir.
Okay, what are you not seeing?
Sir, just go right again.
So you understand that the electronic configuration of oxygen is 2,6. Agreed?
Yes, sir.
Good. Oxygen needs 2 electrons for it to be stable. Agreed?
Yes, sir.
I want to create a diatomic molecule of oxygen, meaning say oxygen can link with itself to form a molecule. So it's going to be 2 oxygens coming together. So it's going to be O2, O subscript 2. Follow me?
Yes, sir.
Oxygen is non-metal. It's really a gas. So when I form that bond, it means then that I'm going to have O and an O to give me O2.
Mm-hmm.
They will have to bond covalently because it's 2 non-metals that are coming up together. So the bonding cannot be ionic and it cannot be metallic. It cannot be metallic or ionic because there's no metal. There is 2 gases, 2
Yes.
non-metals that are reacting, right? So the non-metals react covalently, will bond covalently. So what I'm saying to you is oxygen has 6 valence electrons, both of them, because the same oxygen. How are we going to share those together? 2 of the electrons on each of the oxygen atom will come together and clump together to share each other. So oxygen will say, I will share 2 of my electrons with you. And the oxygen say, okay, fine, and then I'll share 2 with you as well. All right, so they're both sharing 2 electrons each. So in all, it's 4 electrons that are being shared. See it right here, so 1, and that's why I put the dot and cross diagram. If you go into the exam and you hear them ask up dot and cross, it means that one of them is supposed to be crossed and the other one be dot. So that you can see the sharing or the transferring of electrons. That's why we do the dot and cross for. You follow me?
Yes, sir.
Mm-hmm. So now these 4 valence, these other 4 electrons now from either atom will remain unchanged. 1, 2, 3, 4, and 1, 2, 3, 4. There's only these 2
Mm-hmm.
that will be shared with 2 more of it. So what they're going to do is come close together because remember them can't get them up enough. So they're just going to come close together and just attach itself to it. So any energy this atom has, this atom can suck the same energy from it. Low energy, low energy. So they're going to pretty much have the same sort of attribute.
Okay.
Yeah. So that's all that there is to it. I'm going to give you homework. I'm going to send you this. Don't move yet because I want to send it in
the chat?
In the chat, yeah. I want to do chlorine and nitrogen. I want to do chlorine and nitrogen.
The covalent bonding.
Yeah, man.
Do you put it in the chat? Or just
I'm going to do no. I'm copying it out to do that. So. You have another class now?
Yeah, it's something is research. Yeah.
Oh, sir, remember to talk to Doc about the topics from statistics.
You know that she's back from St. Lucia, and I was doing camp road teaching a class, and I called to her, and I had a conversation with her, and I did not remember. I mean, very honest. I can only be honest. I had a good conversation, a good belly laugh with her. So I will talk with her. I'll send her a message.
All right, thanks a million.
No problem. But hold on, don't move yet because I'm sending this thing now. I don't understand. From a couple nights now, I'm trying to, every time I save my document, I'm struggling to. I'm struggling to find it. But why am I struggling to find it? I don't need to struggle to find it, sir. All right, check to see if you see it now.
Yes, sir. I see it. I'm seeing it.
All right, good. So download it for me, please, and then have a good one, right? Let me know when you
Okay, sir.
download it so I can end the session.
Okay. I have downloaded it.
All right, Mikey?
Hold on. It's downloading. Oh, yeah.
All right, pick up yourself. All the best in class.
So, it's
I'm going to
just...
send her a message now.
Okay.
All right, cool. All the
Okay,
best.
sir. Thank you, sir.